So, until now we have been looking at the details of normal shocks. So, we have looked at how to analyze them and get relationship between all the flow parameters in terms of only the upstream Mach number and gamma. Now, let us continue with those discussions and see some more facts about these normal shocks. And so, just to give a quick recap, so the important relationship that we get is that of the Prandtl's relation for normal shocks, which is m1 star m2 star equal to 1, and from this so the main principle used here is that it is an adiabatic flow, and in adiabatic flow the star conditions remain constant, and you apply that condition along with the conservation equations, and you get relationships for density ratio across the shock, temperature ratio, pressure ratio, and entropy ratio, as well as stagnation pressure ratio. Since shock waves generate entropy, the stagnation pressure decreases across the shock. So, now with these information, let us move ahead and look at what are the limiting conditions for the shock wave. So, one thing is clear that the characteristics of the shock depend only on the upstream condition, that is Mach number and gamma. So, if Mach number, upstream Mach number is increased continuously, so the strength of the shock depends on Mach number, and it is generally referred to as the pressure ratio. So, as Mach number increases, pressure ratio increases significantly. So, now let us see what happens if Mach number tends to infinity. So, its limit is known as the strong shock limit, because here the pressure ratio can become really high. So, first let us look at the Mach number downstream of the shock. So, the expression is over here for Mach number downstream of the shock, and Mach number tends to it goes towards infinity. So, you can use the appropriate limit, that m1 square tends to infinity. So, you can sort of take out m1 from both of them, and here you will get 1 by m1 square. So, as m1 square goes to infinity 1 by m1 square goes to 0, and if you apply that particular limit, you see that m2 square tends to a finite value, which is gamma minus 1 by 2 gamma for a perfect gas. Of course, it is for a calorically perfect gas. So, m2 reaches finite values as Mach number tends to infinity. We had an indication of this when we were looking at the graphs of the variables as Mach number, upstream Mach number is increased in the previous class. So, we saw that the downstream Mach number saturates, and the reason is that as it tends, Mach number tends to infinity, m2 reaches finite values, and for air it is 0.377. Similarly, if you look at the density ratio across the shock, rho 2 by rho 1, again this is the expression for rho 2 by rho 1, follow the similar procedure that m1 square tends to infinity, and here also you observe that the density ratio across the shock reaches finite values. This is gamma plus 1 by gamma minus 1, and for air where gamma is 1.4, this is equal to 6. But for all other parameters like the pressure ratio P2 by P1, this as m1 increases, m1 square goes to higher and higher values. Of course 1 becomes very small compared to that. Similarly this also is very small, so it approximates to 2 gamma m1 square by gamma plus 1, which tends to infinity. So pressure ratio goes to infinity, and temperature ratio is nothing but multiplications of pressure ratio and density ratio. So since pressure ratio increases to infinity, even temperature ratio increases to infinity. So this limit that shock waves are becoming very strong as Mach number increases is known as the strong shock limit, and in strong shock limit Mach number downstream of the shock and density ratio reach finite values, but pressure ratio and temperature ratio can increase to infinite values. So what about entropy? Entropy increases to infinity. As a consequence the stagnation pressure ratio which is P02 by P01 is nothing but e power minus delta S by R. So as delta S increases to infinity, P02 by P01 tends to 0. So stagnation pressure decreases to 0. So again let us review the graphs that we had plotted earlier and discussed it. So as per our discussions of strong shock limit, you can see that density quickly saturates here and the value should be 6, and also the Mach number, downstream Mach number saturates to 0.377, while the pressure ratio and temperature ratio keep increasing, and the stagnation pressure ratio continues to decrease and can decrease to 0. So this is a strong shock limit. Now the other side of the spectrum is when the Mach number is very close to 1. So you know that shock waves can be present only in supersonic flows, and that is condition is Mach number should be greater than 1, and the strength of the shock depends on the Mach number. So the weakest possible shock is at Mach equal to 1. So in the neighborhood of Mach number equal to 1, we get the limit of very weak shocks. So let us look at the limit of very weak shocks. So to look at this limit, let us see what is the the entropy change across the shock at very weak conditions. So this is the same expression for entropy written in terms of pressure ratio and density ratios, and pressure ratio and density ratio expressions for the normal shock is known. So we substitute that in this expression over here, and density ratio is substituted here. Now this is in terms of parameter m square minus 1 or m1 square minus 1. This parameter is written as a coordinate or sort of variable transformation is done, where m is equal to m1 square minus 1 or m1 square is equal to m plus 1. So this is to make the analysis feasible. Now as now we are looking at the limit that m1 tends to 1. This is the weak shock limit. So if m1 tends to 1, m tends to 0. So m tends to very small values. So if you now express the equation in terms of m as it is done over here, then you find that these terms 1 plus 2 gamma by gamma plus m or gamma minus 1 m by gamma plus 1, these terms are of the form 1 plus x whole power n, where x is small, x is small now here. So, this can be expanded using the series, that is, this is in terms of log. So, you can use the power series to expand this log of 1 plus x. Okay, the expansion is given over here, and you expand all the terms, 3 terms, and collect the terms together. There will be some algebraic manipulations and cancellations, and ultimately you end up with the term 2 gamma m cube by 3 gamma plus 1 m square plus higher order terms. Now, higher order terms are neglected. Even the first order term, if you look at it, is having a term m cube. That means it varies with the cube of m. Now, m is already a small number, because m1 square minus 1 and m1 is going towards 1. So, you see that as m1 tends to 1, very quickly rapidly delta S, that is entropy change, goes to 0. That means in the weak shock limit, essentially you are reaching isentropic conditions. So, the weak shock limit is almost like that of an acoustic wave or isentropic conditions. Okay, having discussed the strong shock and weak shock limits, let us now look at another facet of these normal shocks, that is the Hugoniot equation. The Hugoniot equation expresses the properties across the normal shock only in terms of thermodynamic variables, and the velocity does not figure in the expression. So, one can look at all possible shock states, and we will see how to do that. Until now, all the expressions for normal shocks had the upstream Mach number in place. So, here we will look at how to write the equations for thermodynamic variables across the shock. So, we have to appropriately combine the 3 equations, and we begin from the continuity equation rho 1 u1 equal to rho 2 u2, and here directly you will get u2 equal to u1 into rho 1 by rho 2. Now, we take the momentum equation, p1 plus rho 1 u1 square is equal to p2 plus rho 2 u2 square. So, we have this equation. Now, here we substitute for u2. So, p1 plus rho 1 u1 square is equal to p2 plus, here you get rho 1 square u1 square by rho 2. Now, p2 minus p1 is you can take this common rho 1 u1 square, and you will get 1 minus rho 1 by rho 2, and this can be written as p2 minus p1 is equal to rho 1 rho 2 minus rho 1 by rho 2. So, p2 minus p1 by rho 2 minus rho 1 multiplied by so this is rho 2 by rho 1 is equal to u1 square. I think that is the expression that we get over here. So, the same analysis can be carried out by expressing u2 u1 in terms of u2, and then getting the equation for u2. If you proceed along the same directions, you get u2 square is equal to p2 minus p1 by rho 2 minus rho 1 multiplied by rho 1 by rho 2. So, you get these two terms, and now we have used the mass and momentum conservation. Now we move to energy conservation, which is h plus u1 h1 plus u1 square by 2 is equal to h2 plus u2 square by 2, and here now h is nothing but E plus P by rho, and if you substitute that you get E1 plus P1 by rho 1 plus u1 square by 2 is equal to E2 plus P2 by rho 2 plus u2 square by 2. Now we have the expressions for u1 square and u2 square just from the previous slide. We substitute that here in these terms, and we get P2 minus P1 by rho 2 minus rho 1 rho 2 by rho 1. Now this can be simplified because you have all the terms related to pressure and density over here, and you have energy terms over here. So now if you express this E2 minus E1, so E2 minus E1 is equal to you get P1 by rho 1 plus half P2 minus P1 by rho 2 minus rho 1 multiplied by rho 2 by rho 1, okay, minus P2 by rho 2 minus half P2 minus P1 by, so you get this term over there. Now from here all we have to do is simplify the right hand side of this equation, and there you can observe that there is the group of terms like this P2 by rho 2 and plus half P2 minus P1 by rho 2 minus rho 1 multiplied by rho 2 by rho 1 minus rho 1 by rho 2. This is what you get. So to do this, this term is nothing but rho 2 square minus rho 1 square by rho 1 rho 2, and here you have the term rho 2 minus rho 1, so this term will come out to be half P2 minus P1 multiplied by rho 2 plus rho 1 by rho 1 rho 2. So now this can be algebraically simplified, and after simplification this is the expression we get: E2 minus E1 is equal to P1 plus P2 by 2 multiplied by 1 by rho 1 minus 1 by rho 2. So E2 minus E1 is the energy difference, internal energy difference across the shock wave, while P1 plus P2 by 2 is an average pressure written here, and 1 by rho 1 minus 1 by rho 2 written if expressed in terms of specific volume is V1 minus V2 as change in specific volume. So change in internal energy is equal to average pressure multiplied by change in volume, specific volume. So this equation is known as the Hugoniot equation, and one can readily see that there is no velocity terms over here. It purely expresses only in terms of thermodynamic variables, and also here when getting to this equation we have never stated any assumptions of perfect gas. So this is valid for a general case. So Hugoniot equation is a general equation, it is valid for shocks in all kind of gas dynamic conditions. So let us look at the plot. So this is a Hugoniot curve, it plots all possible shock states starting from 1, where 1 represents the upstream conditions. So upstream, once you know the upstream pressure and temperature, consequently the specific volume, this point can be located and the Hugoniot curve can be drawn. And now how do we get to a particular shock? If you know a particular velocity, or you know the particular Mach number, for that we draw what is known as the Rayleigh line. This is the Rayleigh line. Rayleigh line just comes about from the momentum equation, P plus rho v square equal to constant. We can use the energy equation to use to combine with this, because rho v is constant across the shock. So if we can express v in terms of, so this is g is another constant, so this becomes p plus g square by rho is equal to constant, or p plus g square specific volume is equal to constant, p is equal to plus c. So this is the equation of a straight line. So Rayleigh lines are straight lines in the PV diagram, and you should also notice that it has a negative slope. G square is positive, so it's always having a negative slope. Now this Hugoniot equation, as we already know, it just uses the conservation equations, and the conservation equations do not specifically say whether a certain thermodynamic state is possible or not. That comes from entropy conditions. So from one we can draw Rayleigh lines going either way, with a decrease in pressure and increase in specific volume, or an increase in pressure and decrease in specific volume. And this is the case of an expansion shock. It is unphysical, so this is not possible, while only the shock wave, which is a compression shock, is possible. So with the help of Rayleigh line, which has the information of velocity, which will figure in the term g square, one can locate a particular shock. So Hugoniot can give you all possible shock states passing through an initial point 1. Okay. So Hugoniot is a general equation. You can use it for any type of shocks in any gas dynamic medium. So now we come to a particular application of the shocks. Until a few classes ago, we were discussing the applications of isentropic equations to the problem of flow measurement and the Pitot, and we discussed the subsonic Pitot, where in a compressible medium or in a compressible flow, one cannot use the Bernoulli's equation, but rather we have to use the condition that you achieve stagnation pressures within the Pitot. Pitot measures stagnation pressure, and the relationship with stagnation pressure and static pressure is given by an isentropic process, and from this one can get the Mach number. So this is for a subsonic Pitot. Now let us go to the condition that the same Pitot, this device Pitot, is uses to measure the flow speed or flow velocity. What happens when we put this Pitot inside a supersonic flow? So it is now very clear that in supersonic flows, if you place some bodies or you put some devices, then from our earlier discussions you should understand that in order for the flow to turn over the body, the flow has to know that the body is present over here. In a supersonic flow, this cannot be accomplished because information does not propagate in all directions. In order to facilitate this, ultimately you get a shock wave. A shock wave envelops the body. This is what is coming over here. So, a shock wave envelops the pitot. So, there is a pitot, there is a shock wave in front of the pitot, and what the pitot measures actually is stagnation pressure downstream of the shock. So, if you take a look at the zoomed in picture, this is the idea over here, that you have the stagnation streamline, it is going through the, right here, and this is the pitot, and very close to the nose of the pitot there is a shock, and this shock is normal to the the streamline at this point. So, one can apply the normal shock conditions across the shock, and the pitot actually measures the stagnation pressure downstream of the shock wave. So, if you put a pitot in a supersonic stream, then it does not measure the stagnation pressure of the stream, rather it measures the stagnation pressure downstream of the shock. And by now it is very clear to us that stagnation pressure decreases across the shock. So, P02 is less than P01 and it is not the same as P01. So, now we have to express just going by the similar measurements. So, how measurements are done usually in some experiments and practically is that usually the pitot is placed inside the duct or within the free stream, and P02 is measured, and you need always one more measurement, that is the static pressure you need to measure, and for that the measurement is usually taken on the walls of the tunnel somewhere where static pressure of the stream can be easily measured. So, this is P1. So, usually the measurement is P02 and P1. The stagnation pressure ratio is expressed for P02 by P2, that is for the downstream conditions of the shock, and it is dependent on M2 square. But we know that all these values P2, P02, M2, all of them depend only on the upstream Mach number. So, they can be expressed as functions of only upstream Mach number. So, that is what is done over here. P02 by P1 is what we are usually measuring, and P02 by P1 is written as P02 by P2 and P2 by P1. P2 by P1 can be expressed in terms of upstream Mach number, P02 by P2 expressed in terms of M2 square, M2 square can be written in terms of M1 square, and so we get this expression for P02 by P1. This is known as Rayleigh's Pitot formula, and this formula is generally given in normal shock tables along with all other equations and the pressure ratios and temperature ratios, because this is a very common measurement that is made, and we would like to know the Mach number. So, once you know P02 by P1 either by using the tables or by using calculators, we can get back what is Mach number. So, this is Rayleigh Pitot formula. So, with this we come to the end of discussions on stationary normal shocks. In this particular discussion we used rho 1 u1 equal to rho 2 u2, P1 plus rho 1 u1 square equal to P2 plus rho 2 u2 square, and H1 plus u1 square by 2 is equal to H2 plus u2 square by 2. So, in all these are conservation equations for a steady flow, and this what is considered is a normal shock is steady in a supersonic flow. Now next what we would discuss is the moving shocks. Shocks can also move. Typical cases that you one can encounter is inside shock tubes, or in cases of explosive events when there is a blast wave. The blast wave also moves rapidly at supersonic speeds. So, we will see how we can analyze such shock waves in the next class.